The Sahara looks permanent, an ocean of sand stretching beyond sight, heat that bends the air, wind that reshapes dunes but never the desert itself. It feels fixed, but it is not. Beneath the dunes lie river valleys wider than modern highways. Satellite radar has traced channels hundreds of miles long, hidden under layers of sand. From orbit, faint arcs mark the shorelines of lakes that once rivaled the largest on Earth. Fossilized fish rest deep in the desert interior. Pollen from tropical plants survives in sediment. Beneath the surface, massive aquifers hold water that fell thousands of years ago. This was not always a desert. Between roughly 14,000 and 5,000 years ago, monsoon rains pushed north. Grasslands spread, rivers flowed. A vast lake known as Megachad expanded to a size comparable to the Caspian Sea. Hippos, crocodiles, and giraffes moved across land that today struggles to support a single tree. But how did a place so lush and green become one of the driest regions on Earth? And if it happened once, could it happen again? Tonight, we move slowly across the surface of the Sahara before we descend into the hidden world beneath it. But before we begin, if you enjoy these peaceful explorations, I would appreciate it if you gave this video a like and subscribed. And if you feel like sharing, I'd like to know where you're listening from and what time it is there. I always enjoy seeing how far these late night stories travel. Now take a slow breath and let's return to the time when the Sahara was still green. Far above the surface of North Africa, long before wind touches sand or heat rises from stone, the governing force of the Sahara begins in the slow descent of air. The desert occupies a vast subtropical corridor stretching from the Atlantic Ocean to the Red Sea, bordered in the north by the Atlas Mountains and fading gradually into the Sahel to the south. Its scale spans millions of square kilometers, yet its defining feature is not simply size, but position within a global circulation pattern. Air heated near the equator rises and releases its moisture in heavy tropical rainfall. Having shed that moisture, it drifts poleward at high altitude before sinking over the subtropics. As it descends across North Africa, it compresses and warms, lowering relative humidity and suppressing the formation of clouds. This descending branch of the Hadley circulation establishes a semi-permanent high-pressure system that restricts precipitation across the region. In some areas, rainfall amounts to less than a single inch in an entire year, and certain stretches may pass multiple years without measurable rain. On the ground, this atmospheric stability shapes a landscape of varied textures. Ergs, or sand seas, extend in sweeping arcs where dunes assemble into crescent forms known as barchans, or into long linear ridges aligned with prevailing winds. Some dunes rise hundreds of feet above surrounding plains, their crests migrating gradually as grains are lifted and deposited in continuous motion. Though dunes shift, the broader desert framework remains anchored by climate rather than by the sand itself. Beyond these sand seas lie regs, gravel-covered plains formed as finer sediments are removed by wind, leaving behind stone pavements that armor the surface. Hamadas present yet another expression, elevated plateaus of exposed bedrock etched by erosion and temperature extremes. Together, these terrains create a mosaic of sand, gravel, and stone rather than a uniform expanse. Moisture scarcity limits biological processes at every scale. Without consistent rainfall, soils remain thin and low in organic content. Plant life survives through adaptations that conserve water, including deep taproots, reduced leaf surfaces, and dormancy cycles triggered by rare precipitation events. When storms do arrive, ephemeral streams may briefly cross dry channels, and short-lived blooms appear before returning heat, and evaporation restore aridity. Organic debris desiccates rapidly, and decomposition proceeds slowly in the absence of sustained microbial activity. Seasonal temperature swings can be dramatic, with intense daytime heat followed by sharp nighttime cooling under cloudless skies. Yet the fundamental driver remains the descending air mass that discourages uplift and condensation. High pressure reinforces clear skies. Clear skies enhance surface heating, and surface heating maintains the cycle of dryness. From the vantage point of a single human lifetime, this repetition conveys permanence. The Sahara appears fixed within its boundaries, defined by enduring atmospheric conditions that feel immovable. And yet, even such stability exists within a broader planetary rhythm, shaped by forces that extend beyond the horizon of ordinary time. The first hints did not come from the ground, but from orbit, where instruments drifted silently above the planet and listened for echoes. Radar pulses traveled downward, passing through dry sand that to the human eye appears opaque and absolute. Instead of reflecting only from the surface, certain wavelengths penetrated the dunes, scattering off buried structures hidden beneath meters of sediment. What returned to the sensors was not randomness, but pattern. Broad curving lines emerged beneath the present desert, sinuous and branching, organized in the unmistakable geometry of river systems long extinguished. As mapping techniques improved, these faint signatures resolved into paleo channels stretching hundreds of miles across North Africa. Some converged into larger trunks, forming drainage networks comparable in scale to modern continental rivers. Subsurface imaging revealed entire watersheds preserved beneath sand seas, complete with tributaries and floodplains. In places, ancient valley walls remained intact, shielded from erosion by the very dunes that covered them. The sand, rather than erasing the past, had sealed it. Satellite derived elevation models exposed subtle depressions aligned with these channels, indicating former basins where water once pooled. Beneath certain expanses of desert, radar uncovered the outlines of deltas, where branching rivers appear to have spread into wider lowlands. These formations suggested that the vanished rivers did not simply fade into the ground, but once emptied into expansive lakes. The scale of the systems implied sustained flow, not isolated storms. Channels carved deep enough to survive burial required repeated discharge across centuries, perhaps millennia. Ground expeditions followed orbital discoveries, drilling cores through dunes to confirm what the radar suggested. Beneath layers of wind-blown sand lay fluvial sediments, rounded gravels, and fine silts deposited by moving water. In some regions, the buried channels aligned with fossil shorelines visible from space, reinforcing the image of interconnected hydrological networks feeding inland seas. The geometry was coherent, integrated, unmistakably shaped by sustained rainfall and runoff. The preservation itself owes much to aridity. In humid regions, vegetation roots, flowing rivers, and chemical weathering constantly reshape terrain. In hyper-arid environments, once surfaces are buried, they may remain undisturbed for vast spans of time. Wind deposits layer upon layer of sand, protecting underlying forms from erosion. What seems like relentless motion at the surface can conceal remarkable stability below. The desert becomes an archive, not through abundance of life, but through absence of disturbance. Seen from orbit, the modern Sahara still appears unbroken and immense. Yet beneath its dunes lie river valleys that once carried water across distances, now measured in silence. Their branching paths speak of gravity, slope, and sustained flow. Their scale speaks of rainfall far beyond present limits. And carved channels of such magnitude are the quiet testimony of a climate capable of nourishing rivers, because rivers do not carve themselves without rain. Long before the dunes settled into their present stillness, the atmosphere above North Africa followed a different rhythm. During a span now known as the African Humid Period, beginning roughly 14,500 years ago and lasting until about 5,000 years before present. Seasonal winds carried moisture far beyond their modern reach. The summer monsoon, strengthened by shifts in Earth's orbital geometry, advanced hundreds of miles northward, where descending dry air now dominates. Rising humid currents once gathered, condensing into clouds that released steady rains across regions that today receive almost none. The transformation unfolded gradually, then with widening consequence. Rainfall totals in many areas approached levels comparable to modern savannas, sufficient to sustain continuous vegetation rather than isolated patches. Grasslands spread across basins that had long been defined by sand and stone. Dunes stabilized as plant roots anchored sediment, reducing wind-driven movement and allowing soils to accumulate organic matter. Shrubs and trees extended their range northward, forming woodlands and corridors that linked highlands to low plains. Acacia, tamarisk, and other drought-tolerant species flourished in environments that were no longer defined solely by aridity. Surface water responded quickly to sustained precipitation. Seasonal lakes formed in topographic depressions, filling during wet months and retreating during dry intervals, only to return with the next cycle of rain. Rivers flowed across terrain that is now etched only by memory beneath sand, integrating drainage networks into expansive watersheds. These rivers transported sediment, carved channels, and deposited fertile layers along their banks. Wetlands emerged where groundwater reached the surface, supporting reeds, fish, and migratory birds. The hydrological system operated not as a rare anomaly, but as a recurring seasonal pattern sustained over millennia. Evidence of this humid phase extends beyond the continent itself. Off the western coast of Africa, marine sediment cores preserve layers rich in terrigenous material washed from inland rivers. Within those cores lie pollen grains carried seaward by runoff, their microscopic structures revealing the presence of grasses and woodland species once widespread across North Africa. Isotopic signatures within the sediments reflect enhanced freshwater discharge, confirming that rainfall intensified across the region during this interval. Lake bed deposits found deep within the present desert align with these offshore records, reinforcing a coherent climatic narrative. This greening was not confined to isolated pockets or sheltered valleys. It reshaped drainage patterns, altered atmospheric feedbacks, and reconfigured ecosystems across an immense geographic expanse. Vegetation increased surface roughness and evapotranspiration, reinforcing regional precipitation in a self-sustaining cycle. Rivers interconnected basins that had once been separated by aridity, creating continuous ecological corridors. What had been dominated by wind became influenced by water, and landscapes reorganized accordingly. This was not a scattered oasis. It was a continent-wide transformation. In the central lowlands of North Africa, subtle arcs curve across stone plateaus, tracing contours that no modern shoreline occupies. These faint ridges, visible from aerial surveys and satellite imagery, outline the margins of a lake that no longer exists, yet once spread across an area exceeding 350,000 square kilometers. Known today as Mega Chad, it filled a broad basin where several ancient rivers converged, transforming interior desert into an inland sea comparable in scale to the Caspian. From high above, its former terraces remain etched into bedrock, concentric lines marking successive stages of expansion and retreat. The basin itself lies within what is now the Chad Depression, a topographic hollow capable of collecting immense volumes of runoff when precipitation intensifies. During the humid interval already described, Rivers flowing from surrounding highlands delivered sustained discharge into this depression. As inflow exceeded evaporation, water levels rose steadily, flooding valleys and submerging plains. Shorelines advanced outward, reworking sediments and depositing layers of sand and silt along gently sloping margins. Wave action carved benches into exposed rock, while deltas formed where tributaries entered the widening lake. Physical evidence persists across surprising distances. Fossilized freshwater mollusk shells have been recovered far from any present water source, embedded in sediments that once lay beneath lake shallows. Their calcium carbonate structures confirm prolonged immersion in freshwater conditions. Core samples extracted from former lake beds reveal laminated deposits rich in diatoms and other freshwater algae, microscopic organisms whose silica shells accumulate in calm aquatic environments. These layers document years of biological productivity, each thin stratum representing seasonal cycles of growth and sedimentation. Remote sensing technologies allow reconstruction of the lake's geometry with increasing precision. Subtle changes in surface reflectance correspond to buried beach ridges and wave-cut platforms. Digital elevation models reveal gentle gradients descending toward the basin center, consistent with expansive standing water rather than isolated wetlands. The scale implies not a transient flood, but a stable hydrological regime sustained over centuries. Yet the history of Megachad was not defined solely by expansion. As regional rainfall patterns shifted, inflow declined. Evaporation, persistent under subtropical sun, gradually outpaced replenishment. Water levels fell, exposing terraces that had formed during earlier high stands. Lake margins retreated inward, leaving behind saline flats and wind-reworked sediments. Geological evidence suggests that some of these transitions occurred over relatively short intervals, measured in decades rather than millennia, indicating sensitivity to climatic thresholds. What remains today is a much smaller remnant, Lake Chad, fluctuating with seasonal rains, but occupying only a fraction of its former extent. Beneath surrounding dunes and gravel plains, however, the larger story endures in sediment, shell, and stone. These inland seas demonstrate the capacity of climate to reorganize entire basins, converting arid depressions into freshwater expanses and then reversing the process with equal authority. Where there is water, life follows. Beneath layers of wind-shaped sediment and within exposed outcrops of ancient lake beds, bones emerge that do not belong to a desert. In the central Sahara, paleontologists have uncovered fossil remains of elephants and giraffes, their massive limb bones mineralized within sediments that once formed floodplains and wetlands. These were not isolated wanderers straying beyond their range. The distribution of fossils suggests established populations sustained by reliable water and vegetation across wide territories. Along the margins of former lakes, the remains of hippos and crocodiles appear in abundance. Their presence indicates more than seasonal pools. Hippopotamuses require substantial bodies of fresh water to regulate body temperature and protect sensitive skin, while crocodiles depend on aquatic habitats for hunting and reproduction. Fossil fish species have also been identified in regions that today are entirely dry, their vertebrae and scales preserved within lacustrine deposits. Some of these species are closely related to fish now found in West African river systems, implying historical connectivity between basins that are presently separated by aridity. Grasslands that expanded during the humid interval provided forage for large grazing herds. Although the exact composition of these communities varied, evidence from pollen records and plant macrofossils indicates extensive coverage of grasses capable of supporting megafauna densities comparable to those observed in modern East African savannas. In ecosystems where rainfall stabilizes above certain thresholds, primary productivity increases rapidly. Grasses convert solar energy into biomass. Herbivores multiply in response to reliable forage, and predator populations follow the abundance of prey. The ecological structure becomes layered, with grazers shaping vegetation patterns and carnivores influencing herd movement. Comparisons to the Serengeti offer a useful ecological parallel, not as replication but as analogy. In both settings, sustained seasonal rainfall supports wide migratory routes and interconnected habitats. The fossil assemblages of the Green Sahara suggest a similarly dynamic mosaic of grassland, woodland, and freshwater environments. Stable, isotopic analysis of tooth enamel from herbivores indicates diets rich in grasses, while wear patterns on teeth reflect grazing behavior rather than browsing alone. Such details provide insight into feeding strategies and habitat structure. Ecosystems respond quickly when water becomes reliable. Within decades of increased rainfall, plant communities can shift, soil profiles deepen, and animal populations expand. Over centuries, these changes consolidate into stable ecological networks. The Sahara during this humid phase was not a marginal refuge, but a functioning biome capable of sustaining large mammals and complex food webs. The presence of megafauna, aquatic reptiles, and diverse fish communities reveals a landscape structured by water rather than scarcity. And, within these thriving systems, alongside the giants that roamed floodplains and grazed open grasslands, humans were there too. Along the margins of vanished lakes, where sediments once dried into firm ground beside reliable water, traces of human presence remain pressed into the earth. Hearth fragments, stone flakes, and clusters of animal bones mark places where hunter-gatherer communities settled close to shorelines that no longer exist. These were not brief crossings through hostile terrain, but repeated occupations tied to seasonal abundance. Archaeological surveys across central and eastern Sahara reveal camps positioned near former inlets and river mouths, suggesting that people organized their movements around predictable cycles of rain and runoff. Fishing tools carved from bone and shaped stone have been recovered from sites that today lie far from any permanent water. Harpoons with barbed edges, polished points, and net weights indicate a sustained reliance on aquatic resources. Some artifacts show wear patterns consistent with repeated use, hinting at knowledge passed between generations. Pottery fragments found in now barren zones contain residues of plant processing and food storage, suggesting that communities were not only mobile but capable of maintaining semi-stable settlements when conditions allowed. The presence of ceramics marks a shift in daily life, allowing storage of surplus and supporting longer stays in one location. Across sandstone plateaus and rock shelters, engravings and paintings depict scenes filled with water and animals that thrive within it. Images of hippos, crocodiles, fish, and cattle appear alongside human figures, sometimes engaged in herding, sometimes in what seems to be ritual activity. These visual records serve as cultural memory etched into stone, preserving ecological context as well as social meaning. The distribution of such art aligns closely with former drainage systems and Paleolake basins, reinforcing the link between climate and habitation. Evidence of early cattle herding emerges during the later phases of the humid interval. Animal bones show patterns of management rather than solely hunting, and isotopic analyses of teeth suggest controlled grazing near freshwater sources. Domestication allowed communities to buffer against fluctuations in wild resources, yet it also tethered movement to the needs of livestock. Burial sites discovered near ancient water sources indicate attachment to place, with grave goods reflecting symbolic and social complexity. The positioning of these burials implies that water shaped not only subsistence, but spiritual geography. Seasonal migration patterns likely followed the shifting edges of lakes and grasslands. As rainfall intensified or retreated, groups adjusted routes, moving along corridors where vegetation remained viable. Climate acted as an unseen guide, expanding habitable zones during wetter centuries and gradually constricting them as aridity returned. The archaeological record reveals resilience and adaptation, yet it also traces a narrowing of options over time. Landscapes that once supported interconnected communities began to fragment, and settlements clustered closer to reliable watercourses. But the green world did not last. Above the quiet transformations unfolding across North Africa, the deeper cause moved with almost imperceptible patience. The shift in rainfall was not random, nor was it born solely from regional currents. It began with the slow geometry of Earth's motion around the Sun. Our planet does not spin upright in fixed orientation. Its axis traces a gradual circle through space, a motion known as precession, completing a full cycle over roughly 23,000 years. This subtle wobble alters the timing and distribution of sunlight received by each hemisphere during different seasons. During the interval that brought sustained moisture to the Sahara, northern hemisphere summers occurred when Earth was slightly closer to the Sun. The increase in seasonal solar radiation intensified land heating across North Africa. Warm land surfaces created stronger temperature contrasts between continent and ocean, drawing moist air masses inland with greater force. The monsoon system, already a dynamic exchange between sea and land, responded to this amplified gradient. Its rain-bearing belt advanced hundreds of miles farther north than it does today, delivering consistent precipitation deep into what is now desert. Enhanced summer insulation did not act alone. As rainfall increased, vegetation expanded across newly moist soils. Grasses, shrubs, and trees darkened the surface, reducing reflectivity and allowing greater absorption of solar energy. This additional heating reinforced rising air currents, supporting further cloud formation and precipitation. Evapotranspiration from plant leaves returned moisture to the atmosphere, sustaining regional humidity and stabilizing rainfall patterns. What began as a shift in orbital alignment evolved into a network of reinforcing processes linking sunlight, atmosphere, and biosphere. Climate feedback loops operated across multiple scales. Increased freshwater input into lakes and wetlands moderated local temperatures, reducing extreme heat and enabling broader ecological resilience. Expanding plant cover limited dust generation, decreasing the amount of airborne particles that can inhibit cloud formation. Each component interacted with the others, creating a state in which the Sahara functioned not as a barrier to moisture, but as part of a humid continuum extending across the continent. Marine sediment records from the adjacent Atlantic preserve indirect traces of this intensified monsoon, with isotopic signatures and reduced dust flux corresponding to periods of stronger rainfall inland. Together with terrestrial evidence, they reveal a coordinated climatic response to orbital forcing. The African Humid Period was not an anomaly imposed from outside, but the predictable outcome of celestial mechanics interacting with Earth's atmosphere and surface systems. These orbital variations unfold slowly, measured across tens of thousands of years, yet their influence can reorganize entire regions when conditions align. The same precessional cycle that strengthened northern hemisphere summers will eventually shift again, redistributing solar energy in a different pattern. The climate system responds to such changes through feedbacks that amplify or dampen initial triggers, maintaining balance until thresholds are crossed. But feedback loops can reverse. The change did not arrive as a single storm or a sudden silence, but as a slow recalibration of the sky. Over centuries, the seasonal pulse that had carried moisture deep into North Africa began to falter. Earth's orbital configuration continued its gradual shift, altering the distribution of summer sunlight across the northern hemisphere. As peak insolation lessened, the temperature contrast between land and ocean weakened. The monsoon, once vigorous and expansive, retreated southward by degrees, shortening its reach and softening its intensity. Rainfall declined unevenly at first. Some basins retained water longer than others, sustained by residual groundwater and delayed runoff from distant highlands. Yet the broader pattern was unmistakable. With fewer seasonal rains, grasses lost their continuity across plains that had once been densely vegetated. Shrubs thinned, tree cover fragmented into isolated stands. As plant density decreased, the land surface reflected more sunlight, reducing localized heating and further diminishing the rising air currents necessary for sustained precipitation. A reinforcing loop emerged, but this time it worked in the opposite direction. Soils that had formed under humid conditions became increasingly exposed. Without consistent vegetation to anchor them, fine particles loosened under wind stress. Dust generation intensified, lofting mineral aerosols into the atmosphere. These airborne particles scattered sunlight and interfered with cloud microphysics, subtly inhibiting rainfall formation. Each season of reduced precipitation amplified the next, tightening the cycle of drying. Hydrological systems responded with visible consequence. Lake levels began to fluctuate more dramatically. Shorelines retreated inward, sometimes gradually, sometimes in pronounced steps preserved within sedimentary sequences. Core samples extracted from former lake beds reveal transitions from freshwater deposits rich in biological material to evaporitic layers containing salts and gypsum, indicating rapid concentration of minerals as water volumes declined. In certain regions, stratigraphic records display abrupt shifts from dark, organic rich sediments to lighter, wind deposited sands, signaling sudden arid pulses rather than purely gradual change. Isotopic analyses from marine cores off the West African margin register increased dust flux during this interval, reflecting expanding aridity inland. Pollen assemblages shift from grass-dominated spectra to compositions favoring drought-tolerant taxa. These independent lines of evidence converge on a narrative of contraction, not merely of rainfall but of ecological resilience. Communities that had adjusted to centuries of relative stability faced narrowing corridors of habitability. Wetlands fragmented, rivers ceased perennial flow. The landscape reorganized under diminishing moisture, and feedbacks that once supported greenery now accelerated desiccation. Over time, dunes reclaimed former grasslands, and dust veils grew more frequent across the sky. The transition from humid expanse to arid dominance was neither uniform nor instantaneous, yet its cumulative momentum reshaped an entire region. The desert did not simply return, it surged. There are moments in Earth's history when change accumulates quietly, almost invisibly, until a threshold is crossed and the system reorganizes itself into a new state. A tipping point is not a single dramatic event, but the culmination of gradual pressures that alter internal balances. In climate systems, these thresholds emerge when feedback loops that once stabilized conditions begin to amplify disturbance instead. The shift can appear abrupt in the geological record, even though the forces behind it may have been building for centuries. During the drying of North Africa, declining rainfall did not simply reduce surface water, it weakened the ecological networks that had reinforced humidity. Vegetation cover, once extensive, acted as a regulator of energy and moisture exchange between land and atmosphere. Plants absorbed sunlight, moderated surface temperatures, and returned water vapor to the air through evapotranspiration. As plant density diminished under decreasing precipitation, exposed soils reflected more solar radiation and released less moisture upward. Reduced atmospheric humidity limited cloud formation, which further suppressed rainfall. The feedback loop that had supported greening inverted, accelerating desiccation. Ecosystems can persist within a range of variability, adjusting to seasonal and interannual shifts. Yet beyond certain thresholds, resilience declines sharply. When grasslands thin beyond a critical density, wind erosion intensifies, stripping nutrient-rich topsoil and making regrowth more difficult. Dust loading in the atmosphere increases, altering radiative balance and cloud microphysics. Lakes that shrink below specific depths warm more rapidly and concentrate salts, stressing aquatic life and hastening ecological collapse. These processes reinforce one another, converting landscapes from one stable configuration to another. In such transitions, gradual drivers can yield outcomes that feel sudden. Sediment cores from former wetlands reveal layers where organic, rich deposits give way abruptly to wind-blown sands. Pollen records show swift shifts from diverse plant assemblages to drought-tolerant species, the pace of visible transformation, measured in decades or a few generations, contrasts with the slow orbital adjustments that initiated the broader trend. This mismatch between cause and effect illustrates how nonlinear dynamics operate within complex systems. Modern climate research identifies similar thresholds in ice sheets, ocean circulation patterns, and tropical forests. When feedback mechanisms reverse direction, small additional changes can trigger disproportionate responses. The history of the Sahara demonstrates how land surface conditions, atmospheric circulation, and biological processes interact to create tipping behavior. What had been a humid regime sustained by reinforcing loops became an arid regime stabilized by a different set of feedbacks. As water bodies contracted and vegetation retreated, habitable zones narrowed, ecological corridors fragmented, and the balance between moisture and heat shifted decisively toward dryness. The transformation was not merely climatic but geographic, redefining where life could persist. As water vanished, humans moved along a narrow corridor of green threading through northeastern Africa. Water continued its steady passage even as surrounding lands surrendered to aridity. The Nile, sustained by equatorial rainfall and highland tributaries far to the south, flowed with a regularity that contrasted sharply with the drying basins to the west. As lakes contracted and grasslands fragmented across the former humid expanse, communities gradually shifted toward this enduring artery. The river's annual flood replenished soils with fine silts carried from distant uplands, renewing fertility in a landscape otherwise constrained by diminishing rainfall. Archaeological records indicate increasing settlement density along the Nile Valley during the later phases of Saharan drying. Small groups that had once dispersed across broader territories began clustering near reliable water and floodplain resources. Seasonal mobility gave way to more permanent habitation as predictability replaced uncertainty. The river's rhythm offered a framework around which agricultural practices could develop. Crops were sown in freshly deposited sediments as floodwaters receded, drawing sustenance from nutrient rich soils without reliance on direct rainfall. Over time, cultivation intensified. Communities learned to anticipate flood cycles, constructing simple basin irrigation systems to retain water longer on fields and extend growing seasons. Channels diverted overflow into adjacent plots, while earthen embankments moderated flow. These early hydrological modifications did not oppose the river, but worked in concert with it, amplifying natural processes through careful observation. The relationship between water level and harvest became central to social organization, influencing labor coordination, storage practices, and emerging systems of governance. The concentration of population along the Nile fostered exchange, specialization, and cultural continuity. Surplus production supported craft development and trade networks extending beyond the valley itself. As settlements expanded, social hierarchies grew more complex, and symbolic systems evolved to interpret the cycles that sustained life. Temples, administrative centers, and burial grounds emerged within proximity to arable land, embedding spiritual and political structures within the geography of water. The drying of the Sahara functioned not merely as environmental background, but as catalyst. As habitable zones contracted elsewhere, the Nile's reliability gained relative significance. Migration toward its banks consolidated human presence within a confined but fertile corridor, laying groundwork for what would become ancient Egyptian civilization. The river's inundation cycles, structured calendars, agricultural planning, and cosmological understanding. Inscriptions and monumental architecture that later defined dynastic Egypt were rooted in a landscape shaped by hydrological constancy amid regional desiccation. Climate thus acted as a quiet architect, redirecting movement and concentrating innovation where water endured. The transformation of scattered communities into river centered societies illustrates how environmental thresholds can guide cultural trajectories without overt force. As dunes advanced across former wetlands, the Nile Valley became a refuge and a crucible, its steady flow nurturing one of the most enduring civilizations in human history. Even in dryness, the Sahara affects the world. Each year, as surface winds strengthen over North Africa, vast plumes of mineral dust rise into the atmosphere and drift westward in pale veils. From orbit, these plumes appear as sweeping arcs extending across the Atlantic, their edges feathered by turbulence as they travel thousands of miles from their source. What begins as fine sediment lifted from exposed soils becomes part of a transoceanic exchange, linking continents through the movement of air. The particles carried within these plumes are rich in nutrients, including iron and phosphorus derived from ancient rock and long weathered sediments. When this dust settles over the Amazon basin, it delivers trace elements that replenish rainforest soils. Tropical rains leach nutrients rapidly from equatorial ground, and without periodic inputs from afar, productivity would decline. Measurements of atmospheric transport reveal that Saharan dust provides a significant fraction of the phosphorus sustaining Amazonian plant growth. In this way, a region defined by aridity contributes to one of the most biodiverse ecosystems on Earth. The journey of these particles also influences oceanic processes. Iron deposited into surface waters can stimulate phytoplankton blooms in certain marine regions, enhancing primary productivity and altering carbon uptake dynamics. These microscopic organisms form the base of marine food webs and play a role in regulating atmospheric carbon dioxide. Thus, mineral grains lifted from desert plains participate in global biogeochemical cycles, connecting wind, ocean, and biosphere in subtle continuity. Atmospheric dust further affects weather systems across the Atlantic. Layers of dry, dusty air, often referred to as the Saharan air layer, can suppress tropical cyclone development by introducing stable air masses and increased wind shear. At other times, dust interactions with radiation modify temperature gradients, influencing storm trajectories and intensity. The relationship between desert aerosols and hurricane formation remains complex, yet observations confirm that the Sahara exerts influence far beyond its geographic boundaries. This outward reach underscores the desert's role as a global climate engine. The same dryness that once expanded across North Africa now generates airborne mineral flux that shapes distant landscapes and oceans. Dust deposition patterns, recorded in marine sediments and polar ice cores, document fluctuations in Saharan aridity over tens of thousands of years, linking regional climate shifts to planetary scale signals. Even in its present state, the Sahara participates in systems that extend across hemispheres. What appears as emptiness from the ground becomes, at planetary scale, an active source of material and energy exchange. Wind lifts particles, currents carry them, ecosystems absorb them. The desert's influence travels invisibly through the atmosphere, nourishing forests, altering storms, and embedding its signature in far removed environments. Beneath the dunes, water still remains. Deep below the sunlit surface, beneath layers of sand and stone that have witnessed cycles of wind and silence, vast bodies of groundwater remain stored within porous rock. One of the largest of these reserves lies within the Nubian sandstone aquifer system, an immense subsurface formation extending beneath parts of Libya, Egypt, Sudan, and Chad. Unlike rivers that carve visible channels or lakes that reflect the sky, this water moves slowly through ancient sandstone, occupying microscopic spaces between grains laid down millions of years ago. The origin of much of this groundwater traces back to the humid intervals already described, when rainfall was abundant across regions that are now arid. During those wetter periods, precipitation infiltrated the soil, percolating downward through permeable layers until it reached confined aquifers. Over time, these waters accumulated in enormous quantities, isolated from the surface by overlying strata that limited evaporation and contamination. In the absence of significant modern recharge, what remains today is often described as fossil water, a term reflecting its ancient origin rather than biological content. Isotopic analysis provides insight into the age of these reserves. By measuring ratios of stable isotopes of oxygen and hydrogen, along with trace amounts of radioactive isotopes such as carbon 14, scientists estimate that portions of the Nubian groundwater infiltrated tens of thousands of years ago. The isotopic signatures differ from those of contemporary rainfall, confirming that this water formed under climatic conditions unlike those prevailing now. Each drop carries chemical evidence of a time when clouds gathered more frequently over North Africa and rainfall sustained broader hydrological networks. In recent decades, large-scale extraction projects have tapped into these deep aquifers to supply agriculture and urban centers. Wells drilled hundreds of meters into the subsurface bring ancient water to the surface, supporting irrigation systems in regions where surface runoff is minimal. From the perspective of modern infrastructure, the aquifer represents a vital resource. Yet, hydrologically, it functions as a largely non-renewable reserve. Recharge under current climatic conditions is negligible compared to withdrawal rates in some areas, meaning that extraction effectively draws down water stored during distant humid epochs. The concept of drinking from a vanished climate carries both practical and symbolic weight. Each well connects present communities to precipitation that fell long before recorded history. The water emerging from pumps may have seeped into sandstone during the same interval that filled paleo lakes and nourished grasslands. It is a tangible remnant of the Green Sahara, preserved in darkness while surface ecosystems transformed. Though invisible from above, these aquifers anchor modern life across portions of the desert. Their existence underscores the continuity between past and present climates, revealing that beneath apparent desiccation lies a reservoir shaped by different atmospheric patterns. The Sahara still holds memory. High on sandstone plateaus where wind moves freely across exposed stone, images endure that no longer match the land surrounding them. In the Tassili Niger Massif of southeastern Algeria, thousands of carvings and paintings cover rock, shelters, and cliff faces preserved by dryness and time. These figures were not created in the desert that exists today, but in a landscape animated by water, vegetation, and movement. The stone retains what the climate has withdrawn. Among the most striking depictions are aquatic animals carved with careful attention to form. Hippopotamuses appear with rounded bodies and open mouths, crocodiles stretch along painted panels, and fish are rendered with fins and tapering tails. Such creatures require substantial freshwater habitats, not ephemeral pools, but rivers and lakes capable of sustaining breeding populations. Their presence in the art aligns with paleohydrological evidence of wetlands and expansive water bodies across North Africa during the humid interval. The artists recorded what they saw, embedding ecological reality into visual narrative. Cattle scenes occupy another prominent place in the rock record. Herds are shown moving in groups, sometimes accompanied by human figures carrying staffs or bows. The detail suggests domestication and managed grazing rather than isolated hunting. These pastoral images occur in regions that are now hyper-arid, far removed from reliable rainfall. The distribution of cattle iconography corresponds with archaeological traces of early herding communities, reinforcing the link between environmental conditions and subsistence practices. Where grasslands once extended across plains, livestock could be sustained. Where aridity later prevailed, such scenes became memories etched into stone. The progression of artistic styles across the Sahara reveals shifts in subject matter that mirror climatic transitions. Earlier phases emphasize wildlife and aquatic motifs, while later engravings increasingly portray camels and desert-adapted animals. This gradual change reflects ecological transformation rather than abrupt cultural rupture. As habitats altered, so too did the imagery chosen for preservation. The rock faces function as layered archives, each superimposed figure adding context to the environmental narrative. Rock art operates as more than aesthetic expression. It preserves cultural memory of rainfall, lakes, and grazing corridors long vanished from the visible landscape. Combined with sediment cores, fossil assemblages, and isotopic data, these images offer independent confirmation of a greener Sahara. The carvings do not quantify precipitation or measure temperature, yet they document lived experience within a climate that sustained water-dependent life. Protected by the same aridity that replaced humid conditions, these stone canvases remain remarkably intact. Pigments derived from mineral oxides resist fading under dry air, and engravings carved into sandstone survive where organic materials would have decayed. In this way, the desert safeguards evidence of its own transformation. Rock becomes a climate archive, carrying forward testimony from a time when water shaped daily life across North Africa. When global temperatures declined and continental ice sheets advanced across higher latitudes, North Africa responded in its own quiet way. During glacial periods, cooler oceans altered atmospheric circulation patterns, weakening monsoon systems and reducing the northward transport of moisture. The Sahara expanded beyond its present boundaries, pressing southward into regions that today support seasonal grasslands. What had once been transitional zones became fully arid, and the desert widened under a sky carrying less vapor. These intervals were marked not only by reduced rainfall, but by intensified dryness. Hyper-arid phases developed as cooler global conditions suppressed evaporation over distant oceans, limiting the formation of moisture-laden air masses. With diminished precipitation, vegetation cover contracted sharply. Soils that had once held intermittent plant life were left exposed, vulnerable to wind erosion. Sand seas grew broader, and gravel plains extended across basins that had previously supported ephemeral wetlands during more moderate climates. The geological record preserves evidence of these expansions. Thick sequences of wind deposited sediments accumulated across North Africa, forming layers that can be traced and dated. Grain-size distributions within these deposits reflect sustained aeolian transport under persistent winds. As vegetation diminished, dust production increased, feeding atmospheric currents that carried mineral particles far beyond the continent. The Sahara, already vast, became a dominant source of airborne sediment during these cold intervals. Signals of this enhanced dust transport appear thousands of miles away in Antarctic ice cores. Within the layered ice, scientists identify microscopic mineral particles whose chemical signatures match North African sources. During glacial maxima, dust concentrations in polar ice rose significantly, indicating intensified aridity and stronger wind systems in desert regions. These distant archives confirm that the Sahara's expansion was not isolated, but part of a coordinated planetary response to shifting climate regimes. Even as ice sheets thickened in the northern hemisphere, fine grains lifted from African plains settled onto Antarctic snowfields, embedding desert history within polar ice. The pattern resembles a slow breathing of the landscape. During humid phases, vegetation advanced and water filled basins. During glacial periods, dryness intensified and dunes migrated outward. Each state left its imprint in sediments, fossils, and isotopic records. The Sahara did not remain fixed in size or character, but oscillated in response to global climatic rhythms linked to orbital variations and greenhouse gas concentrations. These cycles unfolded over tens of thousands of years, expanding and contracting arid zones in measured succession. Seen across this broader timescale, the desert becomes dynamic rather than static. Its boundaries shift, its intensity fluctuates, and its influence extends across hemispheres through dust and atmospheric circulation. The Sahara breathes with the climate cycles of Earth, expanding in cold epochs and retreating during warmer, wetter intervals, an enduring participant in the planet's long oscillation between ice and warmth. Beneath shifting dunes and gravel plains, where the surface now appears stripped of sustained life, there are places where excavation reveals something unexpectedly delicate. In cross-sections of exposed sediment, pale root traces descend through ancient soil horizons, branching and tapering in patterns unmistakably botanical. These are not recent intrusions. They belong to forests that once stood where wind now dominates, their underground architecture preserved long after trunks and leaves disappeared. Fossilized tree roots have been identified within stabilized sediment layers across portions of the central Sahara. Some remain encased in calcareous crusts formed as groundwater evaporated and minerals precipitated around organic structures. Others are preserved as voids within hardened soil, their original tissues replaced or dissolved, but their geometry intact. The spacing and depth of these root systems indicate mature vegetation, not sparse shrubs, but trees with established canopies and access to consistent moisture. Associated pollen grains and plant macrofossils embedded in the same strata reinforce this picture of woodland environments sustained over extended intervals. Radiocarbon dating of organic remnants within these paleosols provides temporal anchors. Samples extracted from charcoal fragments and preserved root material yield ages corresponding to humid phases already traced through lakes and marine cores. These dates confirm that forested conditions developed during periods when rainfall penetrated far north of its modern limit. The alignment of radiometric results with independent climatic indicators strengthens the reconstruction of a vegetated Sahara. Ancient soil layers, known as paleosols, form when land surfaces remain stable long enough for organic matter to accumulate and horizons to differentiate. Beneath present dunes, such paleosols can be observed as darker bands rich in former biological activity. Their structure reveals processes of weathering, nutrient cycling, and microbial transformation that require sustained moisture. In some locations, multiple paleosol layers stack vertically, each representing a distinct interval of stabilization followed by renewed burial under advancing sand. This stratification records alternating phases of greening and aridity in physical sequence. The density implied by these root networks suggests landscapes capable of supporting complex ecological communities. Trees modify microclimates, reducing wind speed at ground level and enhancing soil retention. Their presence would have supported understory plants, insects, birds, and mammals within interconnected habitats. Stable isotope analyses from soil carbon further indicate inputs consistent with woody vegetation rather than solely grasses. Today, these forest traces remain hidden beneath arid surfaces, exposed only where erosion or excavation reveals them. They serve as structural memory embedded within sediment, documenting intervals when the Sahara functioned as more than open grassland. The preservation owes much to subsequent drying, which limited decomposition and sealed organic signatures within mineral matrices. In these buried soils and fossil roots lies tangible evidence that dense vegetation once anchored the land, awaiting rediscovery beneath the quiet drift of sand. Long before excavation tools ever touched the ground, the shape of what lay beneath the Sahara began to emerge through echoes. Remote sensing instruments, orbiting far above the continent, transmitted radar waves toward the surface, and in certain regions, those signals passed through dry sand before reflecting off harder structures below. The returning data revealed contours that no longer appear in visible light, outlines of ridges and escarpments concealed beneath meters of sediment. What seemed flat from the ground resolved into complex relief when viewed through electromagnetic penetration. Subsurface mapping has since exposed networks of ancient drainage basins buried under sand seas. These basins display branching patterns consistent with prolonged fluvial sculpting, complete with tributary valleys and integrated watersheds. Their geometry suggests extended intervals of surface runoff capable of carving channels and transporting sediment towards central depressions. In some regions, radar imagery outlines entire mountain fronts masked by dune cover, their slopes preserved in surprising clarity beneath accumulated layers of wind-blown grains. The preservation owes much to aridity. Once sand advanced over former valleys and plateaus, It shielded them from the chemical weathering and vegetative disturbance that reshape landscapes in humid climates. Without sustained rainfall to incise new channels or mobilize large volumes of sediment, underlying forms remained largely intact. In effect, the desert created a protective blanket, isolating older terrain from active erosion. Geological time paused at the surface, while wind rearranged only the uppermost layers. Digital elevation models derived from radar interferometry allow reconstruction of paleotopography across wide expanses. By filtering out the modern dune field, researchers can visualize buried escarpments and structural highs that once influenced river direction and lake formation. Some of these hidden features correspond to tectonic structures formed millions of years earlier, reactivated as hydrological boundaries during humid phases. Others represent erosional remnants sculpted by water long before the most recent green interval. Ancient drainage divides, mapped beneath the sand, clarify how runoff once traveled across what is now discontinuous terrain. Valleys align with Paleolake basins identified in earlier sections, confirming interconnected hydrological systems that extended across much of North Africa. The scale of these concealed networks underscores the magnitude of environmental transformation. Entire landscapes, complete with their own internal logic of slopes and watersheds, were buried as climate shifted toward sustained dryness. Today, the surface may appear simplified by uniform sand, yet beneath it lies a stratified archive of former topography. Radar surveys continue to refine this hidden map, revealing details that challenge assumptions about permanence. The Sahara's present face is only the most recent layer in a longer sequence of geomorphic states. Beneath drifting dunes rest mountains, valleys, and basins shaped by water and preserved by wind, landscapes frozen in place until technology allowed them to be seen again. Across the Arabian Peninsula, in valleys now defined by gravel plains and salt flats, sediment cores and cave deposits reveal intervals when rainfall reshaped the land in ways that mirror the history of North Africa. Speleothems growing within limestone caverns record phases of increased drip water, their layered calcite bands preserving isotopic signatures of wetter climates. During certain periods aligned with orbital configurations similar to those that once favored the Green Sahara, monsoon systems extended farther north over Arabia, filling basins and sustaining lakes where dunes now prevail. Fossil shorelines traced across the empty quarter attest to standing water that endured long enough to support aquatic life and migrating fauna. Farther east, within Central Asia, paleolakes occupy depressions scattered across regions presently characterized by steppe and desert. In Kazakhstan, Uzbekistan, and western China, geomorphological surveys identify ancient shore terraces and wave-cut benches marking former lake levels. Sediment analyses reveal freshwater mollusks and diatom assemblages embedded within layers, now exposed to arid winds. These basins expanded during intervals of intensified westerly circulation and altered precipitation patterns, responding to the same large-scale climatic oscillations that influenced North Africa and Arabia. As moisture increased, vegetation spread across plains, stabilizing soils and reducing dust emissions. When precipitation declined, lakes contracted and salt crusts formed across their beds. The synchronization of these humid episodes across disparate regions reflects the influence of global climate oscillations driven by orbital variations and feedback processes within the atmosphere and oceans. Changes in Earth's axial orientation and orbital shape redistributed solar energy, altering monsoon strength and shifting storm tracks. At the same time, fluctuations in greenhouse gas concentrations and ice sheet extent modified planetary albedo and temperature gradients, amplifying or dampening regional responses. The resulting pattern was not uniform, yet it displayed coherence across continents. Marine sediment cores and polar ice records corroborate these linkages, showing concurrent shifts in dust flux and isotopic composition during periods of expanded desert or increased rainfall. The deserts of Arabia, Central Asia, and North Africa have each alternated between greener and drier states in concert with these broader climatic rhythms. Their transformations illustrate that aridity is not a fixed condition, but part of a recurring cycle governed by planetary scale dynamics. Seen together, these lost green deserts form a mosaic of climatic memory, extending across latitudes. The Sahara's past is echoed in distant basins and plateaus, each responding to the same slow oscillations in sunlight and circulation. What appears isolated at the surface belongs to a connected system where shifts in energy balance ripple outward, reconfiguring landscapes far beyond a single region. Far beyond the span of recorded history, the same celestial mechanics that once strengthened monsoon rains continue their slow progression. Earth's axis still traces its gradual circle in space, and the precessional cycle that redistributed seasonal sunlight in the past remains active. Over tens of thousands of years, future configurations will again alter the intensity of northern hemisphere summers, modifying the land-sea temperature contrast that governs monsoon strength. In purely astronomical terms, the conditions that once supported a greener North Africa are not extinct but part of an ongoing rhythm. Climate models that incorporate orbital parameters suggest that increased summer insolation at appropriate latitudes could once more favor northward expansion of monsoonal rainfall. Simulations of past humid intervals reproduce many of the patterns preserved in sediment and fossil records, lending confidence to the underlying physics. Yet, projections into the distant future must account for more than orbital geometry. The modern atmosphere contains elevated concentrations of greenhouse gases relative to pre-industrial baselines, altering radiative balance and temperature gradients in ways that differ from earlier cycles. Greenhouse gas forcing tends to warm the planet overall, intensifying the hydrological cycle in some regions while redistributing precipitation in others. Some modeling studies indicate that enhanced warming could amplify monsoon systems, potentially increasing rainfall across parts of North Africa. Others highlight the stabilizing influence of subtropical high-pressure belts, suggesting that warming alone may not replicate the specific seasonal contrasts required for sustained greening. The interaction between anthropogenic forcing and natural orbital variability introduces layers of complexity absent from previous transitions. Vegetation feedbacks would again play a critical role if rainfall increased. As plant cover expanded, surface albedo would decrease, and evapotranspiration would supply additional moisture to the atmosphere, reinforcing precipitation. However, the threshold required to initiate such a feedback remains uncertain. Contemporary land use, groundwater extraction, and atmospheric aerosol loading further complicate predictions. Human activity has modified both the carbon cycle and regional surface conditions, introducing variables that did not shape earlier humid phases. Geological evidence demonstrates that the Sahara has oscillated between greener and drier states multiple times across the Quaternary period. This cyclical behavior suggests that transformation is possible under the right alignment of orbital and atmospheric conditions. Yet the precise timing and magnitude of any future shift cannot be predicted with certainty. Climate systems are sensitive to initial conditions and internal variability, and small differences can yield divergent outcomes over long intervals. The prospect of renewed rainfall across North Africa remains grounded in physical principles, but it is entwined with contemporary influences that blur straightforward analogies to the past. The Sahara exists within a dynamic planetary system, still governed by orbital motion, yet now also shaped by industrial era emissions. Whether future centuries bring gradual modulation or more pronounced change, the potential for transformation endures within the same forces that have guided the desert's history for millennia. As rainfall patterns shifted and grasslands contracted, animal communities responded not in unison but along pathways shaped by geography and mobility. During humid phases, open corridors linked river basins and lake margins across broad expanses of North Africa, allowing species to disperse freely. When aridity intensified, these corridors narrowed. Habitats that had once formed continuous mosaics fractured into isolated pockets surrounding residual water sources. Migration routes shortened, then disappeared, and populations became increasingly confined to refugia where moisture persisted a little longer than elsewhere. Large herbivores, once sustained by expansive forage, faced progressive habitat loss as vegetation thinned. Grazing territories diminished, concentrating herds within shrinking grassland patches. Competition for limited resources intensified, and reproductive rates declined under nutritional stress. Predator species dependent on abundant prey encountered similar constraints, their ranges contracting in tandem with those of herbivores. In such contexts, ecological networks that had thrived under humid stability became strained. Paleontological records from former lake beds and floodplains reveal shifts in species composition corresponding to these environmental pressures. Fossil assemblages show a gradual reduction in water-dependent fauna, replaced by taxa more tolerant of arid conditions. Stable isotope analyses from bone collagen indicate dietary adjustments as available plant types changed. Tooth enamel microwear patterns reflect transitions from mixed feeding to more specialized strategies, suggesting that animals attempted to adapt to altered vegetation structure. Ecological stress markers are also visible in skeletal remains. Instances of reduced body size, increased mortality among juveniles, and evidence of physiological stress appear in some fossil populations from late humid and early arid intervals. Such signals imply that environmental change outpaced the capacity of certain species to adjust. While some animals migrated southward or toward perennial rivers, others lacked the mobility or ecological flexibility required to track shifting habitats. Extinction evidence accumulates in the stratigraphic record. Species once common in North Africa during humid phases vanish from later deposits, their absence marking the end of regional presence. Hippopotamuses and crocodiles retreated to areas where permanent water remained. Other megafauna disappeared entirely from the Sahara as its ecosystems reorganized under sustained dryness. The pattern reflects selective survival rather than uniform loss, shaped by traits such as dispersal ability, dietary breadth, and reproductive resilience. The contraction of habitable space did not occur in isolation, but within a network of climatic feedbacks already described. As vegetation diminished and dust increased, ecological thresholds were crossed that limited recovery potential. What had been a landscape capable of supporting diverse and abundant fauna became one where only specialized desert-adapted species could persist. Adaptation allowed some lineages to endure, yet for others the transformation proved terminal, inscribed in bone and sediment as testimony to the ecological cost of a shifting climate. Each grain of sand resting across the Sahara carries a history shaped by movement, collision, and quiet settlement. Under magnification, individual particles reveal textures and edges that speak of their journey. Some are rounded through prolonged transport, their corners softened by repeated impact. Others retain angular forms, indicating shorter travel distances from nearby rock outcrops. By examining grain size distributions and surface characteristics, sedimentologists reconstruct the intensity and direction of winds that carried them. Coarser grains suggest stronger gusts capable of lifting heavier material, while finer silts point to more sustained, lower energy transport. Patterns of cross-bedding preserved within consolidated dunes record shifting wind regimes over time. Inclined layers form as sand accumulates on the leeward side of a dune, then migrates forward under persistent airflow. When conditions change, new layers stack at different angles, creating a stratified structure that can be read like pages within a geological manuscript. These internal laminations reveal alternating periods of stability and mobility, capturing fluctuations in climate that influenced wind strength and vegetation cover. Layered deposition across broader regions documents pulses of aridity and relative moisture. During wetter intervals, plant roots stabilize surfaces and reduce sand movement, allowing soils to develop. When dryness intensifies, vegetation retreats and dunes reactivate, burying older horizons beneath fresh accumulations. The resulting stratigraphy contains alternating bands of Paleosol and Aeolian sand, each marking a distinct environmental phase. Sampling these layers provides material for optically stimulated luminescence dating, a technique that determines the last time quartz grains were exposed to sunlight before burial. Through this method, scientists estimate when dunes advanced and when surfaces remained stable. Wind direction patterns can also be inferred from dune morphology and alignment. Linear dunes oriented along consistent axes indicate prevailing winds sustained over long durations, while star dunes form under variable directional regimes. Mapping these forms across the Sahara reveals shifts in atmospheric circulation corresponding to broader climatic oscillations. In some regions, fossil dunes lie beneath newer formations, preserving evidence of earlier wind patterns distinct from those operating today. The sand thus functions as an archive, not through written symbols but through structure and composition. Each layer embodies a balance between atmospheric force and surface response. By extracting cores from stabilized dunes and analyzing mineral content, researchers trace sediment provenance, linking particles to specific source regions. Variations in heavy mineral assemblages reflect changes in erosion zones and transport pathways across millennia. What appears as uniform expanse from a distance resolves, under scrutiny, into a detailed record of environmental change. The Sahara's dunes are not static monuments, but dynamic repositories of climatic information. Through grain size, layering, and orientation, the desert preserves a chronology of wind and dryness, offering insight into the rhythms that have shaped its shifting surface. Within sediments that appear uniform to the naked eye, there exist microscopic fragments capable of revealing entire vanished landscapes. Among them are pollen grains, each produced in vast quantities by flowering plants and carried by wind or water before settling into lakes, wetlands, and soil surfaces. Encased within protective outer walls composed of resilient sporopollenin, these grains persist for tens of thousands of years, once buried in oxygen-poor environments. Their shapes, apertures, and surface textures are distinctive enough to be traced back to specific plant families and, in many cases, individual genera. When scientists extract cores from ancient lake beds across North Africa, they recover vertical sequences of layered mud representing successive years of deposition. Each centimeter of sediment can contain thousands of pollen grains embedded within fine mineral particles. By identifying and counting these grains under microscopes, researchers reconstruct shifting vegetation patterns through time. A dominance of grass pollen indicates open savanna conditions, while increased representation of arboreal taxa points toward woodland expansion. The presence or absence of aquatic plant pollen reflects changes in water depth and persistence. These biological signals are complemented by geochemical measurements. Stable isotope analysis of oxygen and carbon within carbonate shells or organic matter provides clues about temperature and hydrological balance. Variations in oxygen isotope ratios correspond to changes in evaporation relative to precipitation, offering insight into rainfall intensity. Carbon isotopes differentiate between plants using distinct photosynthetic pathways, revealing transitions between grass dominated and tree dominated ecosystems. Together, these proxies form a layered narrative of climate variability. Sediment composition itself contributes additional evidence. Grain size distribution within lake cores reflects the energy of inflowing water, with coarser materials signaling stronger runoff during wetter periods. Layers rich in organic content suggest sustained biological productivity, whereas increased mineral dust points towards surrounding aridity and reduced vegetation cover. Magnetic susceptibility measurements further distinguish between terrestrial input and aquatic deposition, refining interpretations of environmental change. Chronology anchors these observations. Radiocarbon dating of organic fragments and optically stimulated luminescence dating of mineral grains establish temporal frameworks within which pollen and isotopic shifts can be placed. By correlating dates across multiple cores from different basins, scientists identify regional patterns rather than isolated events. This synthesis allows reconstruction of rainfall fluctuations across centuries and millennia, mapping the waxing and waning of humid phases with increasing precision. Through such methods, the story of the Sahara's transformation emerges not from a single artifact, but from countless microscopic traces accumulated layer upon layer. Pollen grains serve as botanical witnesses, sediments as stratified memory, isotopes as chemical signatures of atmospheric processes. Together, they translate buried deposits into coherent climatic histories, revealing how rainfall advanced, retreated, and reshaped North Africa long before written records began. There are intervals in Earth's past when climate altered not over millennia, but within the span of human generations, compressing transformation into lifetimes rather than epochs. One such episode is known as the Younger Dryas, a return to near glacial conditions that interrupted a broader warming trend near the end of the last ice age. Triggered likely by disruptions to ocean circulation in the North Atlantic, this cooling event unfolded rapidly, with temperatures in some regions dropping within decades. The shift reverberated across hemispheres, altering precipitation patterns, vegetation zones, and water availability far from its initial source. In North Africa, the Younger Dryas corresponded with diminished monsoon strength and reduced rainfall, reinforcing arid conditions at a time when climate was otherwise trending toward increased warmth. Lake levels declined and grasslands retreated in certain basins, even as other parts of the world adjusted to shifting temperature gradients. The event underscores the interconnectedness of atmospheric and oceanic systems, where perturbations in one region propagate through teleconnections to distant landscapes. Sediment records capture these changes as abrupt transitions between organic, rich layers and dust dominated deposits, marking swift environmental reorganization. Rapid regional shifts such as this challenge assumptions that climate always evolves gradually. Paleoclimate archives reveal that thresholds can be crossed suddenly when circulation patterns reorganize. Ice cores from Greenland show distinct isotopic jumps associated with the younger Dryas, while marine sediments record altered salinity and temperature profiles. These independent lines of evidence align with terrestrial signals of ecological stress, including changes in pollen assemblages and faunal distribution. For human populations living through such intervals, adaptation required flexibility. Archaeological sites in parts of the Levant and North Africa display adjustments in subsistence strategies, settlement patterns, and mobility during episodes of climatic volatility. The younger Dryas may have influenced transitions toward more intensive resource management in certain regions, illustrating how environmental instability can intersect with cultural innovation. While the Sahara's broader humid and arid cycles unfolded over longer spans, abrupt episodes within those trends added layers of complexity to human experience. Lessons drawn from paleoclimate extend beyond historical curiosity. They demonstrate that the climate system contains internal mechanisms capable of producing swift change under particular configurations. Feedback loops involving ocean currents, ice cover, and atmospheric circulation can amplify disturbances beyond initial triggers. The geological record provides evidence that such reorganizations are part of Earth's dynamic equilibrium rather than anomalies. Understanding these past shifts enriches interpretation of present variability. The younger Dryas serves as reminder that climatic stability can give way to rapid alteration when thresholds are exceeded. In the layered sediments of North Africa and the polar archives of ice, the imprint of abrupt change persists, revealing a planet whose atmosphere and oceans respond to forces both gradual and sudden, shaping landscapes and societies in ways that defy simple expectation. Time does not move at a single pace across a landscape. In some moments, it advances so gradually that change becomes almost imperceptible, measured in millimeters of sediment or the slow migration of a dune crest across a plain. In other intervals, transformation compresses into decades, reconfiguring watercourses, vegetation patterns, and human settlement within a single lifetime. The rhythm of change depends on thresholds, feedbacks, and the forces driving them. Across geological history, mountains have risen and eroded over millions of years, shaped by tectonic uplift and relentless weathering. River valleys deepen over tens of thousands of years, carving through rock grain by grain. These processes unfold slowly, building forms that appear stable across generations. Yet within that broader backdrop, abrupt shifts punctuate the record. Volcanic eruptions can reshape terrain in hours. Glacial outburst floods have scoured channels in days. Climate transitions, such as those already described, have altered rainfall regimes within decades, converting productive basins into dry depressions with surprising speed. The Sahara offers its own layered timeline. During humid phases, vegetation, expansion, and lake formation likely progressed over centuries as rainfall stabilized and soils accumulated organic matter. Dunes were anchored gradually by plant roots, and hydrological networks strengthened across successive seasons. Conversely, the return to aridity appears in sediment archives as episodes where lake levels dropped sharply and wind-blown sands overtook former wetlands within comparatively brief spans. Some paleolake basins record water level declines measured not only in millennia, but in human generational time. Optically dated dune sequences reveal intervals of rapid activation following vegetation loss, suggesting that once protective cover diminished beyond a critical threshold, sand mobility intensified quickly. In contrast, the buildup of paleosols and organic rich layers required sustained moisture over longer durations. This asymmetry between the speed of degradation and the tempo of recovery characterizes many ecological systems. Collapse can accelerate under reinforcing feedbacks, while restoration demands stable conditions maintained across extended periods. Human perception often aligns with the scale of a single life, making gradual change feel permanent and sudden shifts feel catastrophic. Yet, Earth's archives demonstrate that both tempos are integral to planetary dynamics. The Sahara's greening unfolded over centuries linked to orbital forcing, while its drying accelerated under feedback loops that condensed impact into shorter spans. Both rates are embedded within sediment, fossil, and isotopic records. Understanding how fast landscapes can change requires attention to scale. Decades capture the human dimension, centuries reflect cultural adaptation, and millennia reveal orbital rhythms. The Sahara embodies all three, its history written across overlapping timescales that remind us change is neither uniformly slow nor predictably abrupt, but contingent upon the interplay of forces shaping land, water, and air. From a distance measured in millions of years, the word permanent loses its meaning. What appears immovable within a human lifetime dissolves into motion when viewed across geological time. Continents drift, collide, and separate. Climates oscillate between extremes. Landscapes that seem fixed are revealed as temporary configurations within a far longer continuum of change. Mountains offer one of the clearest illustrations. Their peaks rise through tectonic uplift as plates converge, pushing crust upward in slow, relentless increments. Over thousands of years, elevations increase almost imperceptibly, yet as rock ascends, it is simultaneously worn down by wind, water, and gravity. Erosion begins the moment uplift occurs. Rivers carve valleys into fresh highlands, glaciers grind surfaces during colder epochs, and chemical weathering alters minerals exposed at the surface. Given sufficient time, towering ranges are reduced to low relief plains, their former heights recorded only in sediment transported elsewhere. The Appalachian Mountains, once comparable in scale to more dramatic ranges, now stand subdued after hundreds of millions of years of erosion. Oceans also advance and retreat in rhythms shaped by climate and tectonics. During glacial intervals, vast volumes of water are stored within continental ice sheets, lowering global sea level and exposing continental shelves. Shorelines migrate seaward, and coastal plains expand. When ice melts under warming conditions, sea level rises, inundating low-lying regions and reshaping coastlines. Marine sediments, deposited far inland, testify to previous high stands, while fossil coral reefs, now elevated above present tides, record ancient shorelines. Over tens of thousands of years, these oscillations redraw the boundary between land and sea repeatedly. Deserts, forests, wetlands, and grasslands participate in the same impermanence. Their distributions depend on temperature gradients, precipitation patterns, and atmospheric circulation that are themselves products of orbital geometry and planetary feedbacks. The Sahara's transformation from humid expanse to arid domain fits within this broader framework. Its present state is neither anomaly nor endpoint, but one phase in an ongoing sequence. Geological time compresses human certainty. A valley that feels ancient may have formed recently in tectonic terms. A coastline perceived as stable may be migrating slowly under rising seas. Even the composition of the atmosphere has shifted dramatically across epochs, altering the conditions under which landscapes develop. Permanence is an illusion shaped by limited perspective. To view Earth through deep time is to recognize motion where stillness seems to prevail. Mountains rise and are worn down. Oceans expand and withdraw. Deserts bloom and dry again. The Sahara's current appearance belongs to a chapter that will eventually yield to another, guided by forces that operate steadily beyond the span of individual memory, reminding us that every landscape carries within it the seeds of transformation. Long after sediments settle and dunes shift beyond memory, another layer of history remains within the human mind. Landscapes are not only physical settings but anchors for expectation. When a climate appears stable across generations, it becomes the silent background against which culture, language, and belief take shape. Seasons repeat with enough regularity that they are woven into ritual and routine. Water flows where it has always flowed, vegetation returns where it returned before, and the horizon holds a familiarity that feels dependable. This attachment to stability arises from lived experience. A human lifetime spans only a fraction of the cycles that govern planetary systems. Within that span, gradual trends often pass unnoticed, while abrupt events leave sharper impressions. Communities adapt to prevailing conditions and internalize them as normal. Agricultural calendars, migration routes, architectural styles, and economic systems are built around patterns that seem fixed. The expectation of continuity becomes embedded in collective memory. Yet the geological and climatic record tells a different story. Regions that appear immutable have shifted repeatedly between states. The Sahara's transformation from humid grasslands to arid expanse occurred within timeframes that intersected with human presence. For those who lived through its drying, change would not have been abstract. It would have meant shrinking water sources, altered animal migrations, and revised pathways of settlement. The psychological weight of such transformation lies in the tension between memory and reality, between inherited knowledge and shifting conditions. There is a tendency to project permanence onto present landscapes because they form the foundation of identity. When environments alter, cultural narratives must adjust. Archaeological evidence suggests that as North Africa dried, human groups reoriented toward more reliable water corridors, reshaping social organization and belief systems in the process. Adaptation was not solely technical but cognitive, requiring reinterpretation of place and possibility. The Sahara teaches that even vast and imposing terrains are chapters within longer sequences. What feels unchanging can yield to forces operating beyond immediate perception. This recognition does not diminish attachment to place, but it reframes it within a broader continuum. Stability is often a temporary equilibrium, maintained by interacting feedbacks that can reverse direction under new conditions. Understanding this impermanence invites humility in how landscapes are perceived. The desert that seems eternal once supported rivers and forests. Grasslands that flourished under consistent rains eventually surrendered to wind. Human societies navigated these shifts, carrying forward memory even as surroundings evolved. The psychological imprint of a vanished world lingers not only in rock art and sediment, but in the enduring awareness that change, however gradual or sudden, is woven into the fabric of Earth's history. Across generations, long after lakes receded and grasslands thinned, memory traveled in forms that did not require written record. Stories carried details of water, animals, and journeys across terrain that later appeared austere. In many regions bordering the Sahara, oral traditions preserve references to ancestral homelands now distant from present settlements. These narratives often describe migrations prompted by environmental change, recounting movement toward more reliable rivers or fertile ground when conditions shifted. Though shaped by symbolism and cultural interpretation, such accounts echo patterns documented in sediment and artifact. Migration myths function not only as explanations of origin, but as frameworks for understanding adaptation. They embed climatic transition within collective identity, linking people to landscapes through remembered transformation. Among pastoral societies, tales of movement with herds across drying plains reflect lived strategies for coping with reduced rainfall. In some traditions, water sources hold sacred significance, their loss or rediscovery woven into ritual practice. The persistence of these motifs suggests continuity between ecological experience and cultural expression. Archaeological continuity reinforces this narrative layer. Material culture found along ancient corridors often aligns with oral accounts of ancestral roots. Pottery styles, burial practices, and tool assemblages demonstrate gradual relocation rather than abrupt cultural replacement. As environmental conditions altered, communities adjusted settlement patterns while maintaining elements of social organization and belief. This continuity across changing landscapes illustrates resilience embedded within cultural memory. Rock art, already considered as environmental archive, intersects with oral tradition when interpreted within living communities. Certain motifs remain meaningful to descendant groups who view them not solely as ancient artifacts, but as ancestral testimony. The coexistence of visual record and spoken narrative strengthens the case that climate change left imprint beyond geology, shaping stories that outlasted the humid phase itself. Cultural memory operates across scales similar to environmental processes. Some details fade quickly, while foundational themes persist for centuries. The transition from wetter to drier conditions in North Africa likely unfolded over spans that allowed experience to be transmitted directly across several generations. Even as physical traces eroded or were buried, narratives retain knowledge of water's former abundance and the necessity of movement when it diminished. In this way, climate memory becomes part of human inheritance. It informs decisions about settlement, resource management, and seasonal mobility long after the initial change. The Sahara's history is thus preserved not only in sediment cores and fossil assemblages, but in the continuity of cultural expression. Oral traditions and migration myths stand alongside geological evidence, each offering perspective on how societies navigate shifting environments. Together, they reveal that landscapes leave marks on culture as surely as rivers carve valleys, embedding environmental change within the stories communities tell about themselves. High above the shifting continents, the geometry of Earth's motion continues its quiet rhythm. The planet does not travel around the sun in perfect constancy. Its axis tilts, its orbit subtly stretches and relaxes, and its orientation traces a slow circle through space. These variations unfold across tens of thousands of years, altering the seasonal distribution of sunlight without changing the total energy received. Such orbital mechanics form the underlying cadence to which ice sheets advance, monsoons strengthen, and deserts expand or retreat. Axial tilt influences how strongly summers warm each hemisphere. When tilt increases, Seasonal contrasts intensify, enhancing summer heating over land masses. When it decreases, contrasts soften. Precession, the gradual wobble of the rotational axis, determines the timing of seasons relative to Earth's position along its elliptical path. At certain phases, northern summers align with closer proximity to the sun, amplifying warmth. At others, they occur when Earth is farther away, moderating intensity. Eccentricity, the slow modulation of orbital shape, adjusts the degree to which these seasonal differences matter. None of these cycles act in isolation. They interact, reinforcing or offsetting one another across spans far longer than individual lifetimes. Climate oscillations respond to these astronomical patterns through feedbacks within the atmosphere, oceans, and biosphere. Ice sheets reflect sunlight and cool the planet, while their retreat exposes darker surfaces that absorb heat. Vegetation alters albedo and moisture recycling, shaping rainfall patterns that either sustain or diminish plant cover. Ocean currents redistribute thermal energy, linking distant regions within a global network. Over hundreds of thousands and even millions of years, these interconnected processes generate alternating phases of glacial expansion and interglacial warmth. Desert regions participate in this planetary choreography. Geological records indicate that arid belts have shifted repeatedly, sometimes shrinking under intensified monsoons, sometimes spreading under weakened circulation. In North Africa, humid intervals punctuated longer dry phases across the Quaternary period. Farther back in time, tectonic reorganizations and atmospheric composition changes created entirely different configurations of land and climate. Deserts that dominate today were once forested, while other areas that now sustain vegetation endured prolonged aridity. This reinvention does not imply randomness. It reflects the operation of physical laws expressed through complex systems. Orbital variations provide the pacing, internal feedbacks shape the magnitude, and geography determines local expression. Over millions of years, continents drift into new latitudes, mountain ranges rise and erode, and ocean gateways open or close, further redirecting atmospheric circulation. The result is a planet in perpetual adjustment, rarely static for long. Seen within this framework, the Sahara's transformations are part of a broader planetary pattern. The desert is neither anomaly nor permanence, but one manifestation of oscillations that have repeated across epochs. Earth continuously recalibrates, responding to celestial geometry and internal dynamics, renewing its surface again and again in forms that feel enduring yet remain transient within deep time. In the early hours before sunrise, when air cools and wind settles into a softer current, the desert holds a stillness that feels almost suspended outside of time. Sound carries differently across open expanses, absorbed by dry grains and dispersed into distance. The surface appears uniform, shaped into ridges and troughs that seem to belong entirely to the present moment. Yet beneath this quiet exterior lies a layered record of motion and memory, concealed under meters of sand. Far below the dunes, fossil groundwater rests within porous rock formations, sealed away from the atmosphere for thousands of years. These reserves accumulated during wetter phases, when rainfall infiltrated soil and percolated downward through sandstone aquifers. Isotopic signatures preserved within the water reveal its ancient origin, linking it to climates that no longer exist at the surface. In some regions, modern wells draw from these deep stores, lifting water that fell under skies very different from those overhead today. Each extraction connects present life to a vanished hydrological regime. Buried shorelines trace subtle arcs beneath the sand, marking the margins of lakes that once expanded across broad basins. Their contours remain etched into underlying bedrock, preserved by the protective cover of wind-blown sediment. Remote sensing technologies detect these shapes through variations in subsurface density and reflectivity, mapping former coastlines that now lie silent and dry. What appears as featureless terrain conceals terraces and wave-cut platforms formed when water stood against rock for centuries. The wind that moves across these ancient lake beds does not erase their history entirely. It reshapes the uppermost layer, redistributing grains into migrating dunes, yet deeper structures endure. Sand can act as both sculptor and archivist, covering landscapes in a mantle that shields them from rapid erosion. Beneath each crest may lie soil horizons, shell fragments, or mineral precipitates deposited when groundwater levels were higher. The desert's calm surface conceals this complexity, presenting a simplicity that belies the intricate sequences below. Modern stillness contrasts with the dynamic processes that formed these hidden features. Aquifers filled gradually under sustained rainfall. Lakes rose and fell with seasonal inflow. Shorelines shifted as water levels fluctuated. Over time, as aridity intensified, evaporation exceeded precipitation and basins dried. Wind assumed greater influence, transporting sediment from exposed surfaces and smoothing irregularities. The quiet now observed is not absence of change, but the result of cumulative transformation. Standing upon the dunes, one encounters only the immediate present, yet every footstep rests above layered chapters of hydrological and climatic variation. The hush carries no obvious sign of rivers or shorelines, but their imprint persists below. The Sahara's surface may appear still, but beneath it lie reservoirs of ancient rain and contours carved by vanished water, reminders that even the quietest landscapes contain echoes of movement and renewal. At the edge of evening, when light fades across the dunes and the horizon softens into muted gold, the Sahara stands as a quiet testament to motion hidden within stillness. Its vastness suggests endurance, yet every layer beneath the surface speaks of transformation. What appears stable is revealed through patient study as one expression within a sequence that stretches far beyond a single era. The desert is not a monument to permanence, but a chapter in a longer unfolding. The record beneath its sands has shown that green worlds can vanish. Rivers that once traced wide arcs across open plains no longer reach the surface. Lakes that supported fish and grazing herds withdrew into memory. Vegetation that stabilized soil and moderated temperature yielded to wind and heat as atmospheric circulation shifted. These changes did not erase the past entirely. They folded it into sediment, groundwater, and stone, preserving outlines of what once thrived. The absence visible today contains echoes of abundance, yet the same evidence suggests that deserts can bloom. Orbital cycles continue their slow progression, adjusting seasonal contrasts and redistributing solar energy. Feedbacks between land, ocean, and atmosphere remain active. Under different alignments, rainfall intensifies, vegetation expands, and hydrological networks revive. The Sahara has occupied both extremes within geologically recent time, alternating between arid and humid phases in response to forces that operate steadily above and within the planet. Its current condition, while immense and striking, is not final. Across these shifts, a pattern emerges in how change unfolds. For long intervals, trends accumulate almost imperceptibly. Moisture declines gradually, vegetation thins, Lakes contract centimeter by centimeter. Then thresholds are crossed, feedbacks amplify new directions, and landscapes reorganize more rapidly. What seemed stable yields to reconfiguration. The rhythm is neither purely abrupt nor entirely gradual, but a combination of slow preparation and accelerated transition. The Sahara's history invites reflection on how environments are perceived. Stability is often a product of limited timescale, a frame that narrows the view to decades or centuries. When extended outward, the same terrain reveals oscillation. Mountains rise and erode, coastlines migrate, climates alternate. The desert participates in this larger choreography, shaped by astronomical geometry and internal dynamics that persist regardless of human awareness. To follow the Sahara's story is to recognize Earth as a system in motion, continuously adjusting, responding, and renewing. Beneath quiet surfaces lie archives of transformation. Beyond present horizons stretch future phases not yet visible. The planet does not remain fixed. It reinvents itself across spans that exceed memory. Within that vast continuity, each landscape holds hidden histories waiting to be traced, layers of time inviting further exploration into the patterns that shape our world.